Okay, welcome everybody. So before starting, some practical stuff. So for PhD students, we have an attendance list. At the end, you can come here to sign. Remember that we will have a coffee, so try to bring your own cup. We'll have some food offered by the Institute. So during the coffee, we will chat more with the speaker of today, but I encourage to ask many questions also during the talk. So today we have Vijay Balasubramanian from University of Pennsylvania. So a few words. He studied at MIT, did a PhD at Princeton with Callan of Callan semantic equation. And I believe he has more positions other than University of Pennsylvania that are too many for me to remember. So he's here because we invited him to speak at the conference IBM Strings that is starting tomorrow. He's opening the conference. And he's an eclectic researcher because he's not only an outstanding string theorist, he also has a research line on neuroscience. So during the coffee, we can chat also about that. So I leave the floor now.
Great, wonderful.
He will talk us about quantum chaos and the complexity of time evolution.
Great, so I'm going to give this talk from my iPad, and I've been told I should sit here and give the talk from there when I'm sitting here, so I hope you'll be able to see and listen. So indeed, my talk today is on the quantum chaos and the complexity of time evolution. And I've listed this enormous set of references here because I really owe my understanding of the subject to other people, to all my collaborators. So in particular, I want to mention Javier Magan, who's taking up a position in Barcelona, with whom much of this work got initiated, and Pavel Saputa, who's a professor in Stockholm. And also there's Onkar Parikar, who's at TIFR now in India, and really almost all of this work was initiated in a series of collaborations with them. So, so thanks to them. Great, so what is the topic of today's talk? It's about complex dynamics in quantum systems. Now, this is a topic which has become interesting or important, especially in the last maybe 10, 15 years, in a variety of fields of physics. So one obvious place is quantum computation, because that's really become a thing, maybe in the last 15 years, maybe no more than that. And in that period, it's very important to understand how complex a computation is. And computation is an evolution of a state. And how difficult is it to do? This is a question that used to be asked in classical computational complexity theory. Now it's very important in quantum mechanics. It's also become important in various parts of condensed matter physics as people look at systems that are out of equilibrium or evolving in time, because you can get various kinds of dynamical phases and changes of the state of a system that are related to the complexity of the state and complexity of the measurements that you're trying to make. Similarly, there's been a lot of progress in characterizing, in an old problem, which is characterizing the distinction between quantum chaos and integrability. And quantum mechanics is a particularly sort of slightly confusing question because, in classical mechanics, chaotic systems are usually highly nonlinear. And if you look at the time evolution equation in quantum mechanics, it's a Schrodinger equation that's linear, at least in terms of the state vector. And so, exactly how should you characterize chaos, et cetera. There's lots of progress of course, over many, many decades. But there's more, which I will tell you a bit about today. And perhaps the most exotic setting where this has become an important question, particularly in the last decade, is in the theory of quantum gravity and black holes. So because this is the most exotic setting and probably therefore least familiar to most of this audience, I want to start out by telling you about this context and why people doing quantum gravity, including me, have become interested in questions of quantum complexity. Okay? So, and what it means for dynamics to be complex. So let's see. So, so to remind you, so most of these questions in quantum gravity related to complexity have arisen in the context of the physics of black holes. Can you see this, by the way? Even in the back? Yeah, okay. Oh, you have a closer thing. Okay, because normally this would be expanded more. Right. So you all know that the basic black hole solution is this one. It's a solution to general relativity. This is the Schwarzschild solution. And you all know that at r equals 2 gm, the solution looks singular but isn't, right? And you can continue through. So we've also known for well on 100 years that you can, well, less than 100 years, but anyway, that you can continue, 80 years, that you can continue the solution through the horizon. And if you do, you find the maximally extended black hole space-time. And that looks like there's an asymptotic region here. Here I'm drawing the conformal diagram of the black hole. And if you don't quite know what that is, it's a beautiful thing, but there's not enough time to explain. This is one asymptotic region, say our universe. Then you pass behind the horizon, and then there's another horizon you can pass behind there and come to another asymptotic universe. The maximally extended black hole is really a wormhole, an Einstein-Rosen bridge between two asymptotic regions. And if you cut it on this surface, it looks like there's a wormhole, there's a horizon, there's another asymptotic region. This is asymptotically flat here. And if you cut it here, you'll find that there's a horizon, there's an interior, there's a horizon. So the interior region between those two horizons is called the wormhole, and between two regions. Okay, so the maximally extended black hole is actually a horizon. This is not formed from stellar collapse, but we're not going to talk about things made from stellar collapse today because they're just messy, and much of the same things can be said, but I want to avoid talking about that. Anyhow, famously, you know, a black hole is an entropy, which is area over 4g Newton h bar, according to Gibbons, Hawking, and many other greats of the field. Okay, so now there are many puzzles about black holes, right? So one is, so if a black hole has an entropy like this, what are the microstates and why can't you see them? Now there's an argument to be made that the reason why you can't see the microstates of a black hole, why it looks like a black hole, right, and seems to have an entropy, is basically that the microstates are too complex. This is the microstates of the gas in this room are too complex to observe using simple observables kind of observation, but written out much more grandly in terms of an even more complex set of microstates. So what is the idea? Just to give you a feeling for how this might arise, let's think about it like this. So imagine I have some black hole of mass m, and just to be precise for the string theorists in the audience, I want to think about this in universes that are asymptotically anti-de Sitter, have a negative cosmological constant, because then there's some dual field theory that I can talk about. So that's just for the specialists in the audience. Anyway, in all of these settings, you can think about the microstate of a black hole as being created by taking the vacuum of the theory and applying some operator to it. That's how you make a state in a quantum theory. Now, the black hole is, of course, very, very heavy. So let's say, so I'm going to use some number n, which is going to infinity, to sort of control the sort of classicality of the theory, or equivalently, how heavy the black hole is. And I'm going to take an operator of dimension of order n squared. The n squared, as opposed to n, is specifically for the string theorists in the audience. This is like the SUN, Yang-Mills theory, et cetera, et cetera, et cetera. Anyway, these are just enormous operators. So ask yourself, how does such a very big operator look like? So in any theory you choose to name, like this description of the black hole, there's some set of fields that may be there in the theory. There's a gauge field, maybe some gauge fields. There's some scalar fields. There's some fermions. And if you wish to make an operator of this dimension, what you do is you construct some long polynomial in the fields, and you put some traces and what have you to make the thing gauge invariant, right? So let's ask ourselves, if I make a very big operator, what do these operators look like? Now, there's a theorem, which is stated here in basically classical information theory, that says that if I take any finite alphabet and I make a very, very long word out of it, that almost all long words look statistically random. Right? There's no way, there's no statistical test based on some finite number of letters, right, that will reveal to you no correlations, nothing in that long string. So almost all long, large operators in any theory that has some finite number of light fundamental fields looks random. So almost all large operators look random. And these are exponentially big operators if you want to build the microstate of a black hole. So in this sense, they're extremely complicated. They're microscopically extremely complicated. There's no structure in them, and therefore you should expect that they're difficult to probe using simple probes. Now, this is a kind of qualitative statement, and you'd like to make this kind of thing sort of really precise to understand what you're trying to say. Okay? There's a related question, another puzzle about black holes, which is, what is the singularity? So that's one, the first question had to do with the entropy of black holes, and I tried to suggest to you that understanding the entropy of black holes has, and why you can't see all those states, has something to do with the complexity of the states. right? A second puzzle is what is the singularity? So this is supposed to be the singularity of the black hole. You can go behind the horizon, and in the future there's a singularity. There's also in the past, because it's a maximally extended black hole. And classically, the curvatures of space-time break down near this, blow up near the singularity, and this means that there's a breakdown of predictability. So is that really the case, right? Is it really true that physics just breaks down? So quantum gravity people would say, hopefully not, right? You'd think not. And so the answer that people have been thinking about in this context is that the chaotic dynamics in the gravitational theory makes the quantum gravity wave function exponentially complex. And they'd like to say that. People would like to say that. And if so, simple probes can't resolve all of that complexity. So if you're building an effective theory, some sort of effective field theory description of the black hole using simple probes, it's going to look singular because you've just left out the necessary resolving power to resolve the complexity of the wave function. So that would be a kind of resolution of what it means to have a singularity that would be satisfactory. And the question is, can they make any progress about that? So people have been batting this idea about for a while. So there's a second reason why the physics of quantum gravity requires some understanding of what you might want to mean by the complexity of a quantum state. Okay, then comes the third thing. So this is a puzzle that is due to Susskind that came up not so long ago, maybe 10 years ago. So remember, I drew this sort of eternal black hole. Here's a singularity, singularity, two asymptotic regions. Well, so you can take slices of this eternal black hole and compute the volumes of the Einstein-Rosen bridge. Okay, so this is a bit technical. So in the context of this ADS-CFT correspondence, this holographic duality between gravity and the field theory that surely all of you have heard about again and again and again in many colloquia and things, there is a statement that any diffeomorph gauge invariant quantity on one side of the duality will have a gauge invariant quantity that's dual to it on the other side. So an example of a gauge invariant quantity on the gravity side is the volume of one of these maximal spatial slices inside the Einstein-Rosen bridge. So then you would think that this gauge invariant quantity ought to have a dual description of some gauge invariant quantity in the dual conformal field theory to the system. But the question is, but the problem then arises that this volume keeps increasing forever, at least in the classical theory, in the semi-classical theory. So the question is, what object, what quantity in a quantum field theory increases forever, at least for exponential time? So usually after the thermalization timescale, everything's settled down and equilibrated and doesn't increase anymore. But it turns out that you can argue that the complexity, in some sense, of the quantum state could well keep increasing past the thermalization timescale. In other words, that the structure in dynamics past the timescale of thermalization, which is in some ways surprising because we normally think of thermalization as everything equilibrates, there's nothing more that really happens, right? So, but the idea is something does happen. Somehow the complexity of the state increases. And okay, so then if so, then that would be the object that's supposed to be somehow dual to the volume. Okay, so I've stated this is a more technical puzzle, technically stated puzzle. Okay, so let's leave out the two predictions. So all of these sort of three puzzles that I have illustrated raise the question, well, I mean, that's all very well. I've used the word complexity many, many times now, but what does it actually mean, right? I haven't actually defined what complexity means. And, the word is used colloquially in 10,000 different senses, so it could mean anything. So really, the first job, if you want to try to take any of this seriously, is to give an actual precise definition that you can calculate with, right? So almost the entire colloquium today is devoted to that, just that. And at the very end, we'll say a little bit about the quantum gravity, come back around the outside in some specific toy model. But really the goal is to define precisely what we might want to mean by the complexity of a quantum state, right? And then I'll discuss many applications, things like random matrix theories and spin chains and quantum dots and things like this, more condensed matter systems where we can actually come to grips with and calculate and understand what it is we want to mean. And hopefully you'll agree that these are a couple of good definitions that one has come up with. Okay? Feel free, of course, to interrupt me whenever you want. If I'm running out of time, then I'll defer the question to the end. Okay. So let's start. So my goal is to talk about what it means to define the complexity of time evolution or of a quantum state. So The first approach I want to think about is to think about dynamics, quantum dynamics as computation. What do I mean by that? Okay. So suppose I'm thinking about classical mechanics, and I have a bunch of, little particles, and they move around in this kind of way. Some move this way, some bounce around. I would call this a kind of simple dynamics because there are lots of independent local changes in the positions and momenta of the individual particles. Now suppose I had a dynamics where I have a bunch of particles, and a little while later, Sibyl over there walks out. Then I would say that this is a complex dynamics because there was correlation, self-organization, emergence, all of these things that are very difficult to understand, for example, in living systems. Right? So the analog in quantum mechanics may be something like this. Suppose you gave me a Gaussian wave packet, right? And it kind of gets a little bumps and evolves a little bit and gets wider. I might say that this is some simple dynamics because it involves some local changes in the state psi. Little by little, you can build up this change in this way. But suppose after a while you have a very wiggly state that's highly locally and non-locally entangled, there's that entanglement at many scales, etc. Then I might be tempted to say that these large local and global changes in non-local entanglement and correlation imply that there was some underlying complex dynamics which would take a great deal of difficulty to reproduce computationally. You would need many, many gates to do that. Right? That's the kind of intuition you might have. So the computer scientists have been thinking about this for a long time, right? And they have been very fond of the idea that the complexity of a thing, in this case for them, it's an algorithm, complexity of an algorithm, simply counts, so the complexity, they would say the complexity of anything, actually, counts the size of the algorithm needed to assemble the object, right? So when I say that, assemble the object from what? You have to make some commitment to the objects you think are simple, okay? And so the idea in computer science is that you tell me what the simple things are, or easy for you to manipulate are, and I will tell you how complicated your object is by telling you how many simple things you need to put together to make the complex. How many Lego blocks do you need to build the Eiffel Tower? That kind of thing. Okay. So the example, going back decades and decades, is Kolmogorov complexity. So Kolmogorov, the great Russian mathematician, said that the complexity of a sequence, here we're thinking of a list of numbers or a list of letters, like the ones I described as creating the operator that creates the black hole microstate. So Kolmogorov would say that the complexity of a sequence is the length of the shortest program, let's say on a Turing machine, right, or whatever else you'd like, that is required to produce it. So random sequences are complicated, but pi and square root of 7 are simple because you can write a simple code to produce all the digits of pi or square root of 7. And again, remember, this is the kind of thing I said about our black hole microstate operators. They would have a very large Kolmogorov complexity. There's no order in them. So really this is understood as if there's order of some kind in a sequence, it's compressible. Right? So that's the idea. Okay? So a related idea goes back to the work of Jorma Rissanen. He's a Finnish information theorist, and it's called stochastic complexity. And he said that the complexity of a message is the size of the smallest code for compressing it, right? So for example, if I want to send you a picture, right? Some JPEG. Well, I don't send a JPEG. There's the actual picture. What you do is you compress it by using the order in the image to compress it to get it smaller JPEG, and you send the JPEG, right? So the JPEG is a measure of the complexity of the image, right? So that is the way Rissanen would have taught. Both of these ideas feed into the notion of circuit complexity, which says, suppose I give you n input bits, then I'm going to tell you, and I need to compute some outputs from those input bits. So there's a class of inputs with n bits, and I wish to compute outputs from that. Then the complexity of my problem class, in that case, is the size of the circuit I need to build in terms of gates. And in terms of how do you quantify the size of your circuit, pick your poison. It could be the depth of the circuit, the width of the circuit, the number of gates in the circuit, and for different purposes, of course, different things may be useful, right? Okay, so these are ways in which the computer scientists have thought about it. So there is a...
Operationally, this is only putting an upper bound to your complexity, because if you practically have to try to construct a circuit that reproduces that, maybe you're not smart enough and you're not able to find the shortest.
Sure. So this is a statement that the complexity is the size of the smallest circuit. Whether you're able to find that is a separate issue. Also, in practice, there's this thing, which is that there's an ambiguity that the size, of course, depends on the choice of computing architecture. And so, you know, the gates we have in a silicon machine are different from the gates you may have, a theorist may have cooked up. So there's clearly issues here of this kind. But this is why what they do is they focus on the question of how a problem class scales with n, because most of those differences turn into facts about an overall coefficient that they will say, I will ignore and not think about. They think in terms of scaling dimension of the problem. Okay. Anyhow, so we are interested in this discussion in the complexity of, in some sense, physical time evolution. So well, if you're doing physics, you might think the locality in space, time, suggests some possible more natural canonical definition of what it means to be simple or complex. No guarantee, because things like duality that mix up locality. But anyway, you might think that the elementary operations you use should be local in space-time, so they're defined at a point plus its derivatives. These things seem natural, because if you want to operate on many things that are far away at the same time, it would take more work for your machine to do that, right? So again, all right. So these are works. One is trying to feel one's way towards the correct definition. As you'll see, as we move along, initially I'll talk about this way of thinking, and I'll tell you how we will define these kinds of define our way through these various possible ambiguities. And then in the second part of the talk, I'll discuss another newer way of thinking about complexity which doesn't have these ambiguities. Okay, so that's going to be our goal. So the idea from computer science is that the complexity of a thing is the minimum number of simple pieces required to build it. So the question is, what are these simple building blocks? And for us, remember that we're going to think about psi, a vector in Hilbert space, and the time evolution is going to be what we're going to treat as a computation. So we take the state, initial state, and we apply the unitary e to the minus iht. Basically, h is the Hermitian, is the Hamiltonian, and we change it in this way, and we want to think about that as a computation. So for us, so computer scientists are often thinking in discrete time, click, 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 click. For us, time is continuous. So if I take e to the minus iht, that operator, well, that is basically e to the minus iht describes a trajectory on the unitary group. So it's that trajectory that we're talking about. Now, as it turns out, in about 2007 or something, there was a guy by the name of Nielsen, a computer scientist, who proposed the following idea. He showed that suppose you compute the geodesic on SUN, right, the unitary group describing time evolution on n qubits. Suppose you computed a geodesic on SUN, starting from the identity, going to e to the minus iht. He showed that the geodesic in a particular metric that I will describe in a moment bounds the size of the smallest circuit, discrete circuit, to build this time evolution operator. So once it's a bound, right? So you compute the geodesic in this special metric, and it'll give you a bound on how many gates you needed to compute this. So that was a very nice result, which basically geometrizes the notion of complexity. Now for us, as physicists, actually the geodesic definition seems almost better, because we don't have discrete time, we have continuous time. So it seems very reasonable to suppose that going, the complexity is defined by, which way, that's the geodesic linked to this. So I'm going to just run with that and see what it gives me, and whether you can get any useful results connecting this kind of idea to more conventional ideas we have in physics, like the spectrum of a theory, and the eigenstate thermalization hypothesis. There's many things that we know about systems that are simple or complex. Is there any connection here with them is what we're going to try to look at. So what is the metric we're supposed to use? We're supposed to decide which directions in SUN, so which operations, are simple or complex. So it could be like local elements, local operations versus non-local operations, or k local operations versus k non-local. K local meaning acting on k bits at the same time. And so then what you do is you take the Cartan killing form, and then you say, great, I'll put the weight 1 for the simple directions and a weight in the complex directions that's going to be growing with the size of the Hilbert space. Okay? So you do that, and then for some large class of metrics, the geodesic here is going to compute for you this bound that I mentioned, and for us it's going to be the measure of the complexity of the system. Okay, and let's just see what we can get with that, is going to be the idea. So far, so good? Okay, I'm going to sit down here because my left arm is getting tired of carrying this thing. Okay, so the first thing we can do is, so now we've reduced ourselves to a technical problem. Compute GD6 in the unitary group, subject to this this kind of metric that penalizes some directions, some actions, transformations as being complex versus simple. So you can do that. So GD6 in the unitary group are widely studied. This is the Euler-Arnold form of that GD6. And then you have to solve the GD6 equation. And then you construct the trajectory as the path-ordered exponential of all the tangents. And then you can compute the length of the GD6. So you take a minimum over GD6, and that's supposed to be the complexity. Okay? So one thing you can immediately show is that if you generate, suppose your Hamiltonian is made out of simple operators. Okay? So you should assume that because, well, it's sort of a bunch of local operators in the system. Then you can show that initially, whatever the trajectory is of the Hamiltonian, that is a geodesic trajectory. That's the shortest trajectory. So initially, your complexity, measured in this way, will grow linearly in time. Okay? Now, how can this end? How can this linear growth end? It can end if there are shortcuts. And there are two kinds of shortcuts. One is there's a geodesic loop, namely, you could go this way, or you could go the other way, and the other way turns out to be shorter. Imagine, for example, SU2. SU2 is a sphere, right? So if it's 2 qubits, then you could go one way, and then if you go past the pole, then it's shorter to go the other way, that kind of thing. So actually, computing geodesic loops on the unitary group is an unsolved mathematical problem. That's because the group is some god-awful fiber bundle that's really complicated to work with. So that's one of the unsolved problems in math, computing the geodesics in the unitary group. So that's going to be hard to do. But there's something else you can do, and that is to compute what are called conjugate points. Right? So this is another obstruction to this linear growth, which goes like this. So this is the technical definition. Let's not worry about it. So suppose the geodesic you start with is not a minimum, right, of the path length between any 2 points, but a saddle point. Then often it happens that you can push that saddle point a little bit, and it will slip over to a shorter one. So that's called a conjugate point, well known, for example, in general relativity, this kind of thing happens, stuff like this. And so you can try to go look for conjugate points. Okay? And so try to see these are, and as it turns out, these things are the first obstructions that appear to the linear growth of the complexity. And what do you do? So again, there's a whole formalism for doing this. So we don't have to go through this formalism, but I'm just showing you it's completely practical. What you do is you start with an initial geodesic, you perturb the trajectory, you solve the Euler-Arnold equation. There's some variant of this called the Jacobi equation that solves for this. Is all classical math. It's all well known, right? Hard, but well known. You know what to do at least, right? So you do that, and we're not going to do that today. I'm just going to tell you what the results are. So the results wind up showing that there are many connections between this formalism that the computer scientists have invented and things we know well in physics. So for example, suppose that the Hamiltonian has an adjoint eigenoperator with some eigenvalue lambda, then you can show that a conjugate point must occur at a time 2 pi over lambda, right? Now, if the operator O is a local operator. And if the operator O is a non-local operator, then you can show that the conjugate point appears at this time 2 pi 1 plus mu over lambda prime. Mu, which is exponential in the entropy, was the dimension of the Hilbert space. So this is a statement about the structure of the Hamiltonian and adjoint eigenoperators, the Hamiltonian. And by studying the physics, therefore, of the system itself, you can determine when this kind of complexity growth will end. There's a second kind of thing you can do like this, which involves sort of zero modes of the Hamiltonian, which we can also skip. Here's a third claim that sort of feels much more physicsy, right? So suppose you have energy eigenstates m and n, and let T alpha be all local generators of the evolution, right, SUN, and T alpha dot be the non-local generators. Then you can show that the linear growth and complexity for any quantum system is a completely general statement, persists for exponential time, and it goes on for exponential time before it truncates, provided this quantity is of order e to the minus twice the entropy of the system. So for those of you who know the eigenstate thermalization hypothesis, there's a very, let's say first of all discuss what this says. What this says is that it's very difficult to go from one energy eigenstate to another energy eigenstate through the action of a simple operator, like a local operator. That to go from energy eigenstate to energy eigenstate, you really need to use operations that are highly non-local or complicated in some way, right? So this is clearly, in some very intuitive sense, measuring how complicated the structure of the energy eigenstates of the system are. And for those of you who know the eigenstate thermalization hypothesis, which is very much used in condensed matter physics, this is very similar in structure to the eigenstate thermalization hypothesis, which is what guarantees in condensed matter systems thermalization, why simple measurements give you sort of thermal expectation values, things like that. That's all justified using something called the eigenstate thermalization hypothesis, and structurally this thing looks very similar. Okay, so in any way, by doing this kind of thing, you can show many different kinds of results for general results for quantum systems, and then by doing proof by example, if you like, by doing many examples, you can establish that for integrable or chaotic systems, the conjugate points of this kind that I've just described truncate the complexity growth in polynomial or exponential time. So in chaotic systems, the growths persist for exponential time, which is the kind of thing that we were expecting from remember from that for the gravity system that we discussed in the beginning. We said that somehow the idea was that there is an object in the field theory which grows exponentially for exponential time. That's well past the thermalization timescale. So at least this is some proof of principle that some notion of complexity can grow for exponential time in some sensible way for chaotic systems well past the thermalization timescale. Okay? So now the challenge with applying this is it's technically difficult, and there are many ambiguities as we've discussed, right? What are the simple operations, right? What versus the complex operations? That's just a choice I made. And I tried to say a reasonable choice is local things are simple, non-local things are complicated. But maybe what we should do is a little bit non-local is still simple, or maybe we should grade the complexity of operations by the degree of locality. There's many things you could wonder about. Okay. So there's some questions about how to apply this to the cases that I described, although it's of direct use in condensed matter systems if you know what you mean by simple operation or complicated operation in a quantum computer, right? So for example, if you think about the kind of quantum computation being done by Quantinium, they use lasers to move around cold atoms from place to place. So if the two atoms are close to each other, then it's simple. And if they're far away, you have to do some work to move the things around. So definitely physical locality is a direct measure of how simple the operation is. So these things have application clearly that kind of thing, but still there are some ambiguities that make one feel like, well, okay, one should think further. So here's a second approach. So this is an approach to defining what you want to mean by complexity, but thinking about the ergodicity of dynamics. And as you'll see, in many ways, it's more intuitive to us as physicists than the idea that comes out of computer science, and also in many ways, it's much, much easier to calculate with. Okay. So classically, we might say that suppose I have a simple integrable dynamics, what does it look like? Well, in the appropriate phase space or something, you'd find that the initial state sort of does these little loops of some kind and perhaps visits some finite dimensional subspace of the Hilbert space. Well, yeah, I shouldn't call it Hilbert space if it was classical, but anyway. So quantum then. So similarly, what do we mean by complex or chaotic dynamics? Well, we might mean that if I have any initial state or most initial states, then they ergodically or densely explore the Hilbert space. Namely, you tell me any point in the Hilbert space, at some point my state is close to it. Right? Would the kind of thing that you would think would make the dynamics a little bit complicated. So you might say that you could define, maybe one should seek to define quantum complexity as the spread of the wave function over time in some basis. So this is a way of thinking about how it's explored the Hilbert space. Right? You're keeping track of you want a basis that allows you to describe how it explores the entire Hilbert space. But the question then is which basis, right? So following the lead going back to Kolmogorov, we might say that you should pick for an initial state psi naught, you should pick the basis that minimizes the spread over time. And why? Because what is a basis? A basis is a Lego block from which you write down a wave function, right? You add up these Lego blocks called the basis elements, and that gives you the wave function. So, if the complexity of a thing is the minimum number of building blocks, I should pick, by this definition, the building blocks that minimize the description of the state, right? So can we do that? So I'm going to do that. I'm going to try to do that, and I'm going to call the spread complexity, the spread of the wave function over time in the minimizing basis. Okay, so I'll describe what that is. And there's a related notion of operator complexity in this very nice paper by Parker et al. Okay. So let's define this object. And as you'll see, while the computer science definition has a longer history, this definition coming out of physics is really much easier for us to understand and manipulate. Okay. So we start with the Schrodinger equation. dt psi gives you h psi. And well, the solution to this is, I could write down as, it's really e to the minus iht acting on the state psi naught. But then what I can do is I can do a power series expansion and write this as psi of t is some power series times in t times psi n, where psi n is the nth power of the Hamiltonian acting on the state. You'll see why I'm writing it in that slightly peculiar way in a little bit. And of course, in discrete time, you don't have the sum. You just have h to the n acting on psi naught. Okay? So I'm really interested in the continuous case, but you'll see that thinking about the discrete time is helpful. Okay. So now, let B be any orthonormal basis. Okay? And so first I'm going to give you my definition of complexity in this way, and then I'm going to figure out what basis to pick. Okay? So I'm going to take P and B to be the distribution in that basis. So basically I take psi of t, the state at time t, project onto the basis, square it, and that gives me the probability of being in any given basis elements. And so I can take that distribution, and from that distribution, I can do various things. I can compute the entropy of that distribution, that's this. Or I can compute moments of that distribution, various kinds of moments of that distribution, like this. And any of these could be a measure of the size of that distribution, how spread out the state is. So a particular moment, the first moment, this quantity, the average position in this distinguished basis that we will talk about in a minute, has turned out to be very useful and important. Right? So that's what we're going to call the spread complexity, though of course all the other objects like the entropy of this distribution are presumably important too. Okay, so what should I pick to be the minimizing basis? So the minimizing basis turns out to be something called the Krylov basis, and that is produced by Gram-Schmidt orthogonalization of the time-evolving state. So you take psi naught, h of psi naught, h squared of psi naught, etc., and you Gram-Schmidt orthogonalize that. And there's a theorem that you can prove that for any basis B, the complexity that I defined in the previous slide, measured in the Krylov basis, is less than or equal to the complexity as measured in any other basis. This is the minimizing basis. And that's true for at least a finite duration and forever if the time evolution is discrete. The proof is trivial in the discrete case. So let me just give you the proof in the discrete case and ask you to believe me for the continuous case, which requires a little bit of analysis, actually. So here's the discrete case. Here's my initial state. So at time 0, I have my state psi naught. So I should pick that state as an element of my basis, because then I need only one basis element. The state evolves, so then I'm going to add the orthogonal component. Now I have two states to describe it in my basis, k0 and k1. Evolves some more, so I add the orthogonal component. Now I have 3 bits to describe it. So clearly, I can't do any better than this. At each step, I'm just adding one more basis element. So this is obviously the smallest basis. Again, the continuous case is a little bit harder to prove, actually. But because you start with an infinite power series in the first place, and it's a bit of a mess. But that said, it's the same logic underlying it. So you see, trivially, this is true. Okay, excellent. Let's see whether we can make any progress with this. So how do we characterize the spread of the wave function? So I need to characterize all of this, and I want to compute the basis and everything. So there are absolutely beautiful techniques to do this, which are many of which are hidden in books and papers going back to the 1960s and so on and so forth. This is a lovely subject. So the first method, so I'll describe many methods, all of which are practical. Right? The first method I'll describe is the so-called Lanczos method or tridiagonalization method. So what you do is you compute the Gram-Schmidt orthogonalization through this sort of recursion formula. This is the Lanczos recursion formula. So we don't need to go through it in detail, but at the end of it, you will wind up writing down a Hamiltonian in this basis, in the special basis. The Hamiltonian takes this form that acting on a given state, basis element kn, it either takes you to kn plus 1 or kn minus 1. So basically, it turns the action of the Hamiltonian in any dimension for any quantum system into a one-dimensional hopping chain with coefficients that are the so-called Langshos coefficients, A, which is the diagonal bit, and B, which is the hopping elements. So any quantum dynamics at all can be reduced to a one-dimensional chain in this way. It's kind of an amazing thing. And you might say, well, that must be difficult to calculate and numerically hard to do and things like this. And indeed it can be, but actually they're efficient numerical algorithms. So what's going on here is that in our youth and childhood, we are taught that you should take, anytime you give me a Hamiltonian, I should diagonalize it and find the energy spectrum. And if I have the energy spectrum, I can do some things with it. The lesson here is if we want to work out the dynamics, it's actually helpful to try diagonalize the Hamiltonian. And there are methods of doing this. So once you've done that, you then work out the wave function as a function of time, and you take these various powers and you compute the complexity. So that's method 1. Okay? Here's method 2. This is a slicker method than the first method. So this involves something called the survival amplitude. So what you do is you take the time evolving state and you compute the survival amplitude, which is the probability that the initial state, that the state at time t is just the initial state, the probability that you're back to yourself. Okay? So now suppose, so that's simply psi naught e to the iht psi naught, yes? So now, if I take derivatives of the survival amplitude, I get all the moments of the Hamiltonian. Okay? And remember that if I have the moments of the Hamiltonian, then using this algorithm, I can work out all these Langshos coefficients. Okay. So what happens is like this. So I have this one-dimensional chain. The probability at time 0 that I'm in k0 is just this. At time 1, this. If I do at time 2, if I want to stay in the initial state, I can go around twice, or I can go over to state 1 or come back to state 1, right? And so on. So you see, what happens is that at time 1, at the initial time, you're just here. At the first step, you just probe A0. At the second step, you probe A0 and B1. At the third step, you probe A0, B1, and A1. So you can see there's a procedure here. You just go step by step, time by time, right? Moment by moment. And then what you'll find is you'll be able to figure out, by just going step by step, time by time, you'll be able to work out all these elements. Another way of saying this is you can take this chain and you unwrap it in this way into this kind of a structure. So this is time 0, this is time 1, this is time 2, etc. Sorry, this is time 0, this is time 1, this is time 2, and these are all the states you can get to. And then at what will happen is that each of these moments of the Hamiltonian, which is one of these probabilities returning to yourself, is a sum of weighted paths to the graph. And so if you know these weighted paths up to some time t, then the next one contributes the next ak or bk. So there's a sort of very simple dynamic programming algorithm for reading off all these coefficients, just in a very systematic way. So the idea here is that you start with the survival amplitude, then you compute the moments of the Hamiltonian, and from that you can read off the Langshos coefficient, and then you can compute the complexity. So that's method 2. So one thing that I'm going to skip telling you about is for a thermal state, for thermal states, it turns out that the survival amplitude is easy to compute. It's an analytical continuation of the partition sum. So if you can tell me the spectrum of the theory, you can compute the partition sum. And if you know the partition sum, from the partition sum, you can analytically continue to give you the survival amplitude, and then you can compute all these moments. So in the end, if you tell me the spectrum, I can tell you, I can solve the entire problem. Okay. So here's yet another way of doing this. So this is even more sophisticated. Suppose you have a theory. It turns out that there's a direct integral formula you can write down for reading out the Langshos coefficients and thereby working out the complexity. And this works at the large n limit. So it takes a Hamiltonian on some finite dimensional Hilbert space, and you take the finite dimension n to be infinite, and you make it bigger and bigger. And so the formula looks like this. So it looks a bit complicated. So to give you how you show a thing like this, okay? So what you do, say, suppose H is a Hamiltonian. I want to tridiagonalize it. These are the AN, BN, the Longshaw's coefficients along the diagonal and the next diagonal. I'm going to assume that this whole thing is a continuous large N limit. That's the one assumption. What is continuous large N? So if I take Longshaw's down the continuum, so I'm going to find x between 0 and 1, and in this way I want a smooth continuous limit for these coefficients, right? So that's that not all theories satisfy. Then what you can do the following. So imagine reading in n is the size of the Hilbert space that you're going to send to infinity. In order to get a continuous large N limit, it must be that these coefficients are actually constant within each block. That has to be the case. Otherwise, you wouldn't get a continuous limit. So, within each block, you know that this matrix has a tuplets form, namely its constants along the diagonal. You can go look up in a textbook the eigenvalues of the of a tuplets matrix, and they take this form. So once you have that, you can just put together this block with this block with this block with this block, etc., and then do a little bit of manipulation, and you will get this formula at the end of the day. So there's an integral formula that you can sort of solve efficiently to go between the density of states and this tridiagonal. This is all trying to show you that these are completely practical methods, well within the range of things people have been doing for decades, at least numerically, to calculate the objects necessary to compute the complexity of the wave functions in the sense of the spreading. There's one more method I'll tell you about, and then I want to tell you about a bunch of examples to finish the talk. So this is random matrix theories. So remember, what are random matrix theories? Random matrix theories are theories where you say that the Hamiltonian is a random draw from some distribution. This is the Gauss. This could be, for example, you have some potential, let's say the orthogonal or unitary or symplectic matrices with some coefficients, etc., and then you draw according to this distribution your Hamiltonian randomly. Now, why would you do this? You would do this because, going back again, what is it, to the 40s, it was understood by people like Freeman Dyson and Wigner and others that if you have a very complex physical system, then a reasonable approximation to the statistics of the energy eigenstates is given by a random matrix. So this was originally done to model the spectra of nuclei, but now we've used it to model chaotic spin chains, QCD, black holes, all kinds of things. Random matrix structures keep appearing again and again and again. So a great deal is known about these things. So for example, it's well known that the distribution of eigenvalues of random matrices takes this sort of form. Lambda I is eigenvalues, and V is the potential of the random matrix theory. So you might ask the analysis, at least for random matrix theory, use these kinds of techniques to write down a distribution, a probability distribution for the Longshaw's coefficients. So this is the spectrum. This is a probability distribution for the eigenvalue. Can I similarly just simply write down an equation for the distribution of the tridiagonal spectrum? And the answer turns out to be yes, and this is the answer. So extending some results of some mathematicians, that was in 2002, in some work we were able to show that there is a general expression for this distribution, and then you can use saddle point techniques in things like the mean Longshaw's coefficients, the statistics, the covariances, and you can work out all of these things, and you can find various answers. So all I've been trying to tell you so far is we defined some notion of the complexity of the spread of a wave function, right, in terms of these Longshaw's coefficients, which are the tridiagonal coefficients of the Hamiltonian. And now I've showed you 4 different ways, right, of computing these things. These are completely practical. The first one is you have to do a recursion to orthogonalize the Krylov basis. The second one involves taking basically the partition sum, analytically continuing it, taking some derivatives and doing some procedure. And the third one involved using this analytical formula and inverting this integral equation. And the fourth one involved doing that plus a little bit more to get the covariances for random matrix theory. So depending on what kind of system you're working with, you can do any of these techniques. So part of the reason I think these techniques have become popular is depending upon the system you're working with. There are many, many, many methods for actually solving the problem. Okay, so what can you do with it? I'm going to skip this third thing. There's one more interesting thing to talk about, but there's no time, so let's skip it. So here's an example. Here are some examples of. So suppose you construct the thermal state in the so-called SYK model. The SYK model is a quantum dot model of quantum chaos, very popular in condensed matter physics and high energy physics over the last decade, or in a random matrix model. And you construct generic initial states in a random matrix model, and you compute this thing that I call the spread complexity. Then what you see is there's some initial quadratic growth, and then there's a linear ramp, linear just like there was in that in the computational complexity approach to complexity, a linear ramp that persists for an exponential time. There's a peak and then comes back down to a plateau. It turns out that by looking at the height of the plateau, you can read off for generic initial states the entropy of the system. You can read off the size of the Hilbert space. Because what basically happens is that late times the wave function has kind of spread out essentially over the entire Hilbert space, right, in this way. And this peak is directly, the existence of this peak turns out to be directly a consequence of level repulsion that is present in chaotic theories. So you can diagnose chaos by the presence or absence of this peak in the spectrum. So that's the first thing. So you can calculate it in a practical way. Here's a second example, just to understand this more deeply. You can consider various kinds of spin chains. So here are two integrable spin chains, and here are two chaotic spin chains. The details are not so important. So what you can do is you can apply, you remember we gave many different ways of calculating all of the Langshaw's coefficients. One was just do it by hand, just work out the details by orthogonalizing the Krylov basis. And the other one was to this analytical formula. So what this shows here is the black lines are those analytical formulae, and the actual exact numerical computation is given in the colors. So you see that both for the chaotic and integrable spin chains, there's a beautiful map. Then on the other hand, if you look at the variance, discover that for the integrable spin chains, the analytical formula is a terrible, but for the chaotic ones, it's a good match. So in other words, these integral formula work for chaotic systems, but not for integrable systems. Okay. So likewise, you can do more examples. So you can do the example of billiard systems. Another class of examples that people study for integrability in chaos is billiards. So what you do is you construct here for triangular billiards, you have a free particle that's moving around inside this system. Ask questions about what its dynamics looks like. There are integrable triangles, pseudo-integrable triangles, and non-integrable triangles. Non-integrable ones show chaotic type structure. Pseudo-integrable are somewhat in between integrable and non-integrable. Then you can work out all of these quantities again, and you see in a detailed way. So on this side, there is the average level spacing ratio. On this side, there's the standard deviation of Langshaw's coefficients, which is a characteristic of chaotic systems. And you see in a clear way a relationship basically between level repulsion, which is one characteristic of chaos, and the variance. So then the variance of the spacing ratio, so when the level spacing ratio increases, you get low standard deviation. So for integrable, non-integrable systems, this is showing you that these techniques match up traditional measures of chaos. Okay, so let's skip that. So finally, I want to finish by talking about the original thing we discussed, which is the late time saturation of wormhole gravity. Now, that is a long and extended subject of its own kind. So what I'm going to tell you about is I'm going to tell you about the logic of what has been done with that. So most of the work that's been done on this so far has really the precise work, as opposed to more speculative work, has been done in a toy model of gravity called the Jakiv Teitelbaum gravity in 2 dimensions. right? So the Jaquiev-Teitelbaum gravity is basically a spherical dimensional reduction of higher dimensional gravity. So you take everything to be spherically symmetric in higher dimensions, and so the dynamics is effectively two-dimensional. So what you do is you write down that effectively two-dimensional theory, and that thing has a duality with that same kind of SYK model, the quantum dot model that I described earlier. So there's a relationship between them. So the logic that's happened in the last year and a half is like, so you consider this SYK model, and from that model you can compute the density of states. So from that model, because you know the density of states, using all the techniques that I described, you can compute the spread complexity. Other authors, specifically Henry Lin and Sheer Sonner and Rabinovici, showed that at early times, the length of the wormholes in these theories of gravity is equal to, I mean exactly equal to, the complexity of the SYK model. So there's an equality there. This is the same thing. So the quantity that I've been describing is the thing that measures the length of these wormholes in these theories. At infinite n, we're able to show this at an infinite classical limit. So you really want the answer in some finite situation, in some situation which has a quantum gravity as opposed to number n, which is like 1 over h bar, and keeping it finite. So the strategy you can follow is, well, we already know the match at infinite n. So here's what let's do. Let's, for finite n, namely for a finite h bar, let's use our formulae relating the Lang's coefficient to the density plus random matrix theory to work out what the correct answer should be for the full quantum. You details and you discover the full size. If you agree that even in the fully quantum, you extrapolate the classical result to the quantum system, you get to the late arising from the space. So this is the kind of thing that you wanted to get in the first place. So, all right, so basically the logic is at early times, the wormhole length, you extrapolate the late times the quantum theory using the techniques we described. Over possible length of the wormhole, and this leads to a late time breakdown of the continuum effective theory. So that seems to be the reason why I haven't sort of spent the whole talk talking about that is this isn't the very special case of two-dimensional gravity. So really, this will become a result about gravity if we can extend this to the full higher dimensional theories of gravity that we really care about. But this is the preliminary that the techniques that I was describing are precisely the things you need to resolve all of these conjectures in quantum gravity. So let me finish. Recently, in the last decade, there's been much talk about quantum entanglement of underlying degrees of freedom related to connectedness in space geometry. So a thing that's been added to that group of ideas is the idea, one of the things you have to think about is the complexity of the if you're using probes and you have very complex, you can't actually read out the details of the state. So you lose information because you can't read the details of the state. So to define all of that, you need to understand what you mean by the complexity of the state, and what I described today in some detail was what's been done in the recent past to try to resolve those things. So there are many next steps that you could take. Here's one, and this is my last slide. So one thing that people are thinking about is trying to use these kinds of ideas to resolve space-time singularities. So let me review again the kinds of things that we said. Well, the idea is that the underlying theory explains the finite black hole entropy, the saturation, late saturation of the interior volume, and explains that there is a discrete finite dimensional entropy is finite. The effective theory, which is what we do by doing quantum field theory on a black hole background, has a continuum spectrum and information. 8 times of quantum gravity states. That really, when we define effective field theory, we usually think about low energies, slow momenta, things like that. But we also need to pay attention to the fact that we're usually talking about low complexity probes in the sense that we're talking about simple operators, low order correlation functions, and things like that. But at late times, that kind of description becomes hopelessly inadequate because the quantum state has become extremely complicated in the ways I described, and therefore those probes we're used to simply do not resolve the content of the state. So, okay, I'll stop there for today. Thanks.
Thank you, Vijay. Any question?
So I'm wondering how is the relation of the spread complexity and the upon of exponents defined in terms of, is there a direct relation?
Yeah, so in the very early time regime, you can show, you can manipulate the formula for the spread complexity to show an exponential growth with a coefficient that's related to the coefficient that appears in the OTOC, in the out-of-time autocorrelation. So the Lyapunov exponent kind of description, or equivalently the out-of-time auto description in quantum mechanics, has to do with the very early time part of this, so as opposed to the late time part of this. So here we've been mostly interested in the very late time part of the dynamics past the thermalization timescale, because many of the puzzles we care about and the possible new phases of matter that appear are after that timescale. So, but so I didn't do that today, but at early times you can manipulate this formula to wind up looking like well, there's a piece in it that will involve that coefficient, the Lyapunov exponent.
What happened with this late time description in terms of these scramblons of Kitaev?
The scramblons?
Yeah.
I don't know what the scramblons are.
Well, it's an effective theory to describe scrambling. Yeah.
I see.
Yeah.
So I don't know the scramblons, so I can't give you a direct answer. But what I can say is that the scrambling time is also early compared to all of this. Scrambling and thermalization are related. So those are, from this perspective, sort of early times and not probing the late complex state of the system. So another way of thinking about why you might be able to get things that act scrambled already at early times is there's the notion of pseudo-randomness. So pseudo-random states are states that you can build that are quick to build, but are very difficult to distinguish from actually random states by using simple probes. So pseudo-random things exist. And I would imagine that what goes on at the scrambling time, although this hasn't been shown by anybody, is that the states become pseudo-random at that time already, but they haven't become actually close to random, as in they haven't become fully complex yet. So that's what I'd imagine would be happening, but I actually don't know what scramblons are. So.
My question is that is there some study of the relationship of complexity with phase transition?
Yeah.
Because, if you have the probability of the Lanczos coefficients, and therefore you have the density of eigenvalues, and behavior of these eigenvalues, of course, has to do with phase transition and with the behavior with temperature.
Absolutely, that's an excellent question. So the study of that, the relationship to phase transitions, is in its infancy. So people have not applied this in great detail to, for example, if you're on one side or other side of phase transition, how do the Lanczos coefficients change in those phases for the states that are associated with that. So that's not really been studied. There may be some things, but which I'm not really aware of. However, you know that there's been a lot of work on measurement-driven phase transitions in the recent past. You measure. There's some connection between that and what's being discussed here, because those, because you're sort of tickling the state in various ways. I also don't. I don't think that's been fully. I don't understand fully the connection, and that's not been fully understood. But both these things are I think, important and exciting directions that will be developed over the not so distant. I've heard people talking about this would be nice to do and everything. It's, what would be good is to have, before one starts doing numerical studies on very complicated systems, what we need is solvable examples where you can be on this side of the phase transition or that side of the phase transition, study the dynamics. What's that? QCD is an intimidating subject. You really think we can do this in QCD? I'm not so sure about QCD. because I think that's a hard problem. But there are lots of spin chain-like things that have localization transitions and delocalization transitions. One could study those things, so that's for sure. So I suspect that's where the initial progress will be made. One would like to see this in QCD. Partly I got into this game in the beginning myself because there was a nuclear theory friend of mine who kept going on about we need to understand these things in QCD. So yeah, but I think that'll be harder to do.
Okay, thanks for this very stimulating talk. I have, well, maybe 1.5 questions because there's 2, but they may be related. All the time you've been talking about just a pure state Schrödinger equation evolution. Do you think you get any more out of these ideas if considering like the mixed state density matrix, and also is this, you have some recipe for constructing a particular basis? Does this have might this have any application to like quantum measurement problem?
Yes.
So collapse of the wave function.
Okay, these are both very good questions. So there is in fact work doing talking about the analog problem with density matrices. I'd refer you to some of the work of Pavel Saputa in particular, and there are others too. There hasn't been I would say, a completely dramatic difference or a new insight per se, but that may just be because of the choice of initial state. The reason why I'm saying this is that the results I chose to show you today involve generic initial states, right? Like thermal states, random states in which the coefficients in the energy eigenbases are random, things like this. But actually, it's interesting to think about things that are more structured, because even if I think about pure states, remember, okay, let's think about a problem in classical chaos. So think about the kicked rotor. If you think about the kicked rotor, then for some choice of parameters, it's kind of chaotic for for all initial conditions. But for some choice of parameters that are islands of chaos, some initial conditions are chaotic and some aren't, things like this. So that goes to say that the choice of state can matter, and the choice of density matrix can matter, right? So I don't think that's been fully explored. There's just a lot of systems and a lot of things to play with, but there could be something. So I can't quite say. There's been some work on open quantum systems also, and trying to do this kind of thing with Lindblad evolution, appropriate to rather than Hamiltonian evolution, as appropriate to an open quantum system. So that's also work that I'm not fully familiar with. Regarding the quantum measurement problem, do you mean with regard to, what do you mean by the quantum measurement problem? Do you mean sort of stuff like collapse the wave function? What basis should he choose that to be? Yeah, so I don't think that there's been work per se on quantum measurement in that sense. That's an interesting point you're raising. So this is a distinguished basis. So given some initial state, there is a distinguished basis in which to describe its evolution. So does that mean that measurement in that you could make measurements that are indicator functions for elements of that distinguished basis? Is there something interesting that happens if you think about those kinds of measurements as opposed to other kinds of measurements that are incoherent relative to this basis? So I'm not sure. That's something to be thought about, but I don't have an answer that's direct to your question.
Thank you for the instructive talk. I have a very general question. Does high complexity always correspond to high entropy?
Well, okay, so there's some definition necessary there. So suppose I'm talking about a pure quantum state, right? Then regardless of whether it's simple or complex, it has zero entropy in the sense of von Neumann, right? The density matrix, there's no entropy there. So you have to tell me something about the measurements that you're willing to do. That's sort of not unrelated to the earlier measuring question. So if you define for me some set of measurement operators and ask relative to that set of measurement operators, is this high or low entropy, right? Then I would expect that a highly complex state, if you're picking what I might call simple probes, right? So somehow a few local operators, a small number of operators that are reasonably local, then I would say that you would get a high, the complex state would act like a high entropy state relative to those observables. So if that's an adequate answer to your question. So we might think about that in various ways. Here's one way. So I think that if you have complex structure in the state, if you can't resolve it using your observables, then you might as well treat that state as an ensemble of everything that contains which differs in the stuff you can't measure, right? It'll act equivalently. So if you kick the state using some simple probe, any one of these states should be these other complicated states should be equally easy to get into, because that's the nature of the probe you're doing. So you will be effectively computing some kind of inclusive cross sections into all of those things that will act like it has an entropy. So that's the idea. These are words I'm saying. An explicit demonstration of some of these things would be good. And part of the reason, so somewhat unusually for a colloquium, where colloquia usually are supposed to be pretty pictures and comforting words. So I gave you quite a lot of technical detail today. The reason I gave you a lot of technical detail today is these are completely practical methods. If you're interested in that question, you can just do it, right? The only limitation is you have 24 hours and so many people working on things. But this can be done. It's a very, very practical thing to try. Just to mention.
Okay, thanks.
No, can you go to the slide with the, you mentioned the eigenstate thermalization hypothesis. I think some other attendants already asked you similar questions, but I just want to go some details. Because even if I'm here, you only have the diagonal matrix element, which will not vanish at large time. But in principle, it will depend on the initial states, right? Because you may have the diagonal matrix element, but from different eigenstates. Then it stay there. Then how can you say it will thermalize eventually?
Okay, so perhaps I haven't. You will stop me if I have not properly understood your question, right? But so let me first of all make one distinction that perhaps I didn't make clear enough between the first and the second part of the talk. In the second part of the talk, it was all about you pick a state and you ask how it evolves, and then at some level you've got to look at different initial states, and different initial states could work differently. The first part of the talk didn't actually look at states at all. It talked about the time evolution operator. It's a statement about the operator, right? So it's not a statement about the particular choice of initial state, it's a statement of the operator, right? And so the statement here being made is that if you remember, and the complexity here is defined in terms of how easy it is to build the time evolution operator using simple local operations, if you like. And the statement is that you will not be able to build the time evolution operator out of simple local operators, right? You will not be able to approximate, this is not an approximation theorem, so you will not be, the easiest way to build the time evolution operator is just to multiply the Hamiltonian out many times, is what's being said here, if this criterion holds true. And this is a statement about the energy eigenstates, so that's a statement also about the Hamiltonian, and it's a statement about the different generators of transformation that you deem to be simple or complex. So this is a statement about the operator, not about the state. I should have emphasized this. The first part was about operators, time evolution operators, and the second part was about how states change.
Right, but if we focus on this operator, then we start with some initial time, right?
Yes.
You do time evolution.
Yes.
And even if the off-diagonal matrix element will vanish, we just want to measure the eigenvalue of this operator. It's okay, right? Then you study the real-time evolution of this partition value.
So this is not an operator per se, right?
Okay.
This is, well, you can make it, I suppose, but this is a set of numbers that you calculate, right? This is a set of numbers you calculate from the energy eigenstates and from the generators of SUN.
Okay.
So,
yeah, no, I think my question is more related to the eigenstate thermalization.
yes.
Right? Then there actually you have, but okay. So you mentioned it, but you actually don't study the.
No, we're not studying it. So the reason we're calling it eigenstate complexity hypothesis in homage to the people who've gone before us, right? They have defined a criterion
Right.
which looks, something like this. Not quite, right? There's an RMN, which is the, right? I mean, there's the overlap between the energy eigenstates with simple operators. So they would put a simple operator
Right.
between two energy eigenstates, compute some overlap, and that overlap has a diagonal piece. It has this off-diagonal piece, which is suppressed. So it all feels vaguely similar, but the powers are off, by the way. That's an e to the minus s, not an e to the 2 minus 2. I mean, there's some differences. But clearly it feels like there's some similarity here, right? But it's not the same.
Oh, okay. Then I guess, yeah, my question is more related in that context.
Yeah.
Vijay, how do you deal with systems that have topological sectors
Yes.
that you cannot access by continuous evolution from
Yes.
one particular
Well, you have to separate them. So if there's a symmetry in the system that protects bits of the dynamics from other bits of the dynamics, you have to separate this out because that's effectively they're just separate. I mean, so, yeah.
But if the system has topological transitions, for instance, like can happen in gravity?
It could yeah. So if it has what do you mean by topological transitions in gravity?
Well, that you can change the topology of the whole space-time, for instance.
That would be lovely to do. I don't know of a single example when someone's done that dynamically. I've tried myself, and I keep asking people, why don't you do this dynamically? But no one's done it. Is there, I don't know why. But it's suppose you have, right? I mean, so because, for example, if you think about the conifold, this, that, and the other, those are all things that no one has taught me how to roll through a conifold, for example. It'd be a nice thing to do. Okay, but suppose you can do that. Then there are many questions that arise, right? So one question that arises is, sometimes the correct or the easy variables to describe the system after the transition are non-local in the variables that you had before. So that's a kind of duality transformation. So this kind of picture with these operators is not invariant under that, because what you call a simple operator or complicated operator would be different in the two cases. The state description is supposed to be more invariant under that, because you pick the sort of minimizing basis over all possibilities. But I don't quite know how to think about, suppose you go through a transition of that kind, what would happen? So I put a sneaky caveat into all of those things, saying that at least for some finite time, put some at least. So this is the minimizing basis, at least over some finite duration, over this, over that. That's because all the proofs were done by using Taylor expansions of different kinds, which will surely break down if you go through a topological transition. So I suspect what would happen is that the minimizing basis would change when you go through the transition. No one has studied an example where that actually happens, and therefore thought carefully about what needs to be done. So again, what would be nice is a worked example. Doesn't have to be in gravity. Some example where a system goes through some kind of interesting topological transition or something, so that the minimizing basis changes in character, and maybe the second basis is non-local in the first. I don't know. That would be very nice to have. But I think what we need is a worked example in order to be able to train our thoughts and come up with a general rule. So I don't know what the general rule would be.
Very good. I suggest to leave further questions for the coffee. Let's thank Vijay again.